Now that we've seen how blocks are used and connected in Simulink, let's get back to our mathematical model of the falling ball. Remember, we've got the gravity as acceleration, the velocity as integral of the acceleration over time, and the position as integral of the velocity over time. Fortunately, our library within Simulink provides an integrator block that carries out exactly the integration we need. Thus, we can complete our implementation of the mathematical model that we've done so far. Patrick, can you just complete it? Here you see we've got the acceleration and the accelerating force, and then we can...
Yeah, basically we don't see the acceleration as a signal, we only see it as a gain right here. What we have right here, by the way, using a double click, I can enter a name here, and this signal I name FG, gravity force.
The force induced by gravity, exactly.
Yeah. I want to add some more, so I remove the display. From the force here to the acceleration, I have to divide by the mass. So right here, 1 over 0.2. The result of this, I increase this a little bit so we can read it.
Yes.
The result of this, that's now our acceleration. I can call it G for Earth acceleration or A for acceleration.
A for acceleration is a good value,
and
a good name.
If we have a look at that, we had the discussion, do we need the mass or do we not need it? Right here we add the mass, and right here we take it out again. So,
so
we could as well have started with a constant G.
So a constant G will be our acceleration, which is now the result of our computation.
Exactly. So now we want to know the velocity. Therefore, I add an integrator block right here.
Okay.
And what's coming out there is our velocity V.
Okay.
V. And if I add another integrator block,
you just copy and paste it using Control C and Control V keyboard shortcuts.
Yeah, that's faster than going through the context menu. Right now we have right here our position S. And it would be nice to see these signals. I don't want to use a display block right now because this will change over time.
Yes.
Therefore, I use a scope block. And to be honest, I would like to see A, V, and S all in the same scope.
Yes, that's very interesting to see all these parts of the model.
From a single input, I transferred the scope to multiple input.
You opened that window just by double-clicking on the scope symbol.
Right. Yes. Now I click on this gear wheel.
Yeah.
And right here, number of axes I change to 3.
Okay. Now we've got a scope with 3 inputs.
And now I can start the connecting. Let me move this a little bit down. So. And I increase the scope a little bit. This will look nicer. So
yes, okay.
Does it snap? No, I have to do it by hand here. So right here, the velocity V.
You connect them backwards, starting from the sink in the scope, and connect them backwards to the lines, connecting gain and integrator, or connecting the integrators.
Exactly. So now we can run this thing and double click on the scope. It's already here. I make it a little bit bigger, and this icon here gives me an autoscope, so it automatically scales so that we can see the things right here. Right here we see our acceleration A.
Okay, here exactly, it's a little less than 10, so it's 9.81.
But you know what I don't like? I would like to see that it's A. let me give this one try here. This should be a setting here. Legends.
Yeah. Yeah, here it is. You see
Yeah,
the acceleration,
right here we have
the
A,
velocity,
V, and S.
the
So
position.
this is nicer. So once again the auto zoom, and right here we have our constant acceleration, an increasing velocity, and a parabolic increasing position.
Okay, great. Great representation of our simulation values.
Peter, finally we have got an implementation of our mathematical model of our falling ball.
Yeah.
We compute the acceleration, integrate the acceleration to get the velocity, integrate the velocity to get the position.
Okay.
It's as simple as that.
Yeah, that's great.
And you don't have to know any derivatives or antiderivatives in order to do so.
That makes simulation really convenient. Using this model, we can now answer questions like how long will the ball fly until it touches the ground, or how fast will it be when it touches the ground? You can answer these questions in the quiz section of this unit.